so let's go ahead and get started. So today we're going to be continuing talking about circuits. And so last time we did this packet, which was really kind of an overview of one way to approach circuits. But in a certain set of circumstances, there's another way to approach circuits. So the last time we were looking at how we could apply the junction rule and the loop rules. Today we're going to continue a little bit with that, but we're also going to be looking at how we can do circuit analysis by finding what's called the equivalent resistance, or in the case of capacitors, the equivalent capacitance. And so to start out with, I want to lay out a couple of equations. So the first equation is what's called Ohm's law. This is something we've used already, but we'll list it here as well. And so what this says is that the change in potential, or the voltage across a resistor, is going to be equal to the current that flows through it times the resistance. The next equation is the equation that tells you what the resistance is for some resistor, and that's to say that the resistance is going to be equal to rho, which is the resistivity. So this is some property of the material, times L, the length of the resistor, divided by the area. And so you can consider some resistor that looks like this, where this is the area, this is the length, and it has some resistivity of rho. Okay. Now, when we want to talk about how we can add capacitors and add resistors in series and in parallel, we'll define those a little bit more later. But what I'd like to do is I'd like to lay out these equations, and the way that I like to do this is in terms of a chart. And so for this chart, here we can have the line for resistors. This is going to be the line for capacitors. This is in series, and this is in parallel. So in series, resistors just directly add, so the equivalent resistance is just going to be equal to the sum of the resistors. So when I say something's in series, it's like having them sequentially one after another. So an example of a series circuit could be something like this. Okay. Whereas in parallel, the resistors are going to add such that 1 over the equivalent resistance is going to be equal to 1 over the first resistor plus 1 over the second resistor. And in principle, you can have more as well. Okay. Now, a parallel circuit is going to look something like this. And so what's meant by parallel is that the current kind of has a choice of where to go. It can go through this first resistor, call this one R1, or it can go through the resistor R2. Okay, so that's how resistors are going to add in series and parallel. Capacitors actually add exactly the opposite way, and so that's to say that in series, capacitors add 1 over CEQ is equal to 1 over C1 plus 1 over C2. And in parallel, capacitors are going to add according to CEQ is equal to C1 plus C2. Okay, so those are all the equations that we'll be using today. There's one more actually. And that last equation has to do with the power. And so that equation says that the power dissipated through a resistor is going to be equal to the current that flows through the resistor times the voltage across the resistor. Now this can also be rewritten in a number of ways by taking V and plugging it in here. And so what we could see is that if we wanted to express this in terms of the current and the resistance, you would say that this is going to be equal to I squared R, or we could re-express this in terms of the voltage and the resistance. So take this equation and solve it for the current, and then plug it into here, and then you see that this is going to be equal to V squared divided by R. Okay, so those are going to be our equations for today. So let's go ahead and start with our questions. So this first one has to do with the way that we can talk about current in terms of charge per second. And so this says my laptop charger is rated at 2.5 amps, meaning that while operating, it supplies my laptop with this current. How many electrons travel through it in 1 hour? Okay. So things that you need to know here is the units of amperes are going to be charge per second, and the charge of an electron something that we've talked about a couple of times. So just to remind you, the charge of an electron, E, is going to be equal to 1.6 times 10 to the negative 19 coulombs. Okay, so go ahead and talk about this one, and then we'll solve it afterwards. All right, so let's go ahead and talk about this one. So what we're given here is that this laptop charger has a current of 2.5 amperes. So let's write that down, 2.5 amperes. And the unit of amperes is going to be a coulomb per second. Now, what we'd like to do is to figure out how many electrons flow through this laptop charger in an hour. And so what we need to do is first what we can do is we can convert this, instead of having it 2.5 coulombs per second, we can convert this to coulombs per hour. And so when we do that, what we can say is in 1 hour, there are 3,600 seconds. And the other conversion we need to do is we need to convert this from coulombs to electrons. But we know that in 1 electron, there is 1.6 times 10 to the negative 19 coulombs. And so what that means then is we can write 1e divided by 1.6 times 10 to the negative 19 coulombs. And when we do this, we end up seeing that this gives us an answer of 2.3 times 10 to the 22. Electrons. Okay? All right. So let's move on to the next one. Was that not what you got?
No, C.
You got C. Okay. Well, this is my fault for trusting the key again. Let's see. So, our good friend Google here, 2.5 times 3,600 divided by 1.6. That would give us the pre-factor anyway. 56. It should be 56. Yeah, it should be C. Okay. Okay. So the answer is C, which means I need to switch this over to, this one's incorrect, that one's, oh, you know what? I was looking at the wrong slide. Oh, it was, okay. It was C, I was looking at the wrong slide. So it wasn't that, I just can't read. Okay. So not to give away what the next answer is. Okay. All right. So now let's look at this one. So this one says the diagram shows a simple circuit inside a flashlight with a switch and a light bulb. When the switch is closed, current is allowed to flow. At the location of the light bulb, the direction of the current is blank and the electrons flow blank. So follow this diagram that we have here to answer what the direction of the current is and what the direction of the electrons moving is going to be. Let's talk about this one. So what do we say? What do we say? Yeah, C? Both left? So it's true that the electrons are going to flow left, right? But conventionally we define current differently than the way that the electrons flow. So what do you say? We say it's B, right? So when we define current, we say that current's going to flow from the positive terminal to the negative terminal, okay? Which is actually the opposite of the way that the electrons are actually flowing. We say that's the direction that the electric field is pointing is the definition. Did I make another mistake? No, this is the current goes right, electrons go left. Yeah. Okay. Oh, I see. This is at the location of the light bulb. Right. Okay. Yeah. Okay. Good. Okay. So on to the next one. Now, this one involves thinking about one of the equations that I have written here, specifically this one. So this question says, which of the following wires has the lowest resistance? Assume the wires are made out of the same material. So if they're made out of the same material, that means that they have the same resistivity. Okay. So what you're meant to consider is the differences in the diameter of these wires and the lengths to try to determine which one has the most or the least resistance in this case. All right, so this one was pretty easy, pretty straightforward. So what we want to say here is that the resistance is going to be related to the resistivity times the length divided by the area. And so all of these have the same resistivity because they're made out of the same material. The shorter ones are going to have a smaller resistance, right, because R is directly proportional to L. And the ones with the larger area are going to also have the smaller resistance. And so what we want is the one with the largest area and smallest length. And so that's answer choice B. Now, we can kind of think about this conceptually and compare resistance to like a pipe, right? So if you think about current as like the flow of water, which one of these is going to give it the easiest time going through? So it's definitely going to be the one with the largest cross-sectional area, right? Because you're not constricting the flow as much. But you could also say it doesn't have to go as far in B as it does in D. So that's another way that you can think about how this, this is how you can conceptually think about resistance. Okay. Moving on to the next one. This one says two cylindrical resistors A and B have the same length and the material makeup. The cross-sectional area of A is twice as large as the cross-sectional area of B. The voltage applied across each resistor is the same. How do the resistances and the currents compare to one another? Okay, so this one requires a little bit more calculation, but it kind of follows the same idea. All right, so let's go through this one. So we're told for these two resistors that the area or the cross-sectional area of resistor A is twice the cross-sectional area of resistor B. And so from that, what we can infer is that the resistance of A, RA, is going to be half the resistance of B. Okay? Now, when we have these resistances established, we can establish what the current is through each resistor because we said that we connect this to some voltage, and it's the same voltage across both of them. And so if the resistance of A is half the resistance of B, when we apply V is equal to IR, we end up seeing that the current through A is going to be twice the current through B. So the answer should be B and I. Okay, let's move on to the next one. The way that it's set up, it takes either one. Okay. Was there a question?
Yeah, I was just wondering if you could show that like more.
You want me to show it analytically?
Yes, please.
Okay. So if we write down explicitly what RA is, then we have, this is going to be rho L divided by A, and RB is going to be rho L divided by 2A. Now we can take a ratio of these two, so I can divide one by the other, and so this says that RA over RB is equal to a half, and so I can rearrange this, and so this gives me RA is equal to a half RB, okay? Now, in order to find the currents, I have two separate equations for the voltage, right? So V is going to be equal to IR, but really this is VA is equal to IA RA, and we have a second one, VB is equal to IB RB, okay? Now, both of these voltages are the same, right? Now let's plug in what our resistances are here, both in terms of RA, let's say. So if this one's just RA, then RB is going to be RA divided by 2. Or sorry, it's 2 times RA, right? So this is going to be equal to IB times 2RA, okay, which is equal to V. Okay. Now, the V's are the same, and so what I can do is I can say that this is IARA. I can cancel my RAs, and so what I see is that IA is equal to, what am I doing wrong here? No, this is right. IA is going to be equal to 2 IB. Okay. Yeah. Okay. Second guessing myself here, but that's how you can show it through with all the steps. Okay, everybody happy with that? Okay. All right. So now, our next question. This one's a little bit more calculationally intensive, but what we're kind of building up to is to be able to talk about these equations that I had listed at the top here for adding resistors in series and parallel. And so this question says a holiday goose is cooked in a kitchen oven for 4 hours. Assume that the stove draws a current of 20 amps, operates at a voltage of 220 volts, and uses electrical energy that costs 0.068 dollars per kilowatt hour. How much resistance do the heating coils provide? Okay, so that's the first question. All right, so let's go ahead and talk about this one. So we know what the voltage of this oven is, and we also know what current it draws. So in order to find what the resistance is, what we can say is that V is equal to IR. Solve for R, so R is going to be equal to V divided by I, which in this case is going to be 11 ohms, okay, because we had 220 over 20. Okay, let's move on to the next one. Hello, I'd like a different question. Oh. Hold on a second. Hold on a second. Okay, well this next question. Hold on. This next question was supposed to be calculating the power. So, and it's marked correctly here. So this is calculate what the power is. The answer choices are the same, just put it in units of watts instead of ohms. I don't know how that happened. It's not open. It's not my day today, guys.
It's just pulling close.
Yeah, I see it, but okay. Well, we can actually just skip to this question because it involves calculating the power first. So well, I'm not going to tell you how to do it, but we want to know how much it costs to cook the goose. So what we see in this problem is we have these three resistors that are in a circuit with a 12-volt battery as shown. Let resistor R1 be 3 ohms, resistor 2 be 2 ohms, resistor 3 be 4 ohms. We want to calculate what the total resistance, or what's often called the equivalent resistance of this circuit is. So go ahead and take a moment to do that. Okay, so I'm probably going to have to ask harder questions than this one, right? So you can almost just do, everybody should actually be able to do this in their head, right? So to find the equivalent resistance here, we have this equation for adding resistors in series, and so that's just directly adding them together. And so that says in this case, we have resistor R1, which is 3, plus resistor 2, which is 2, plus resistor 3, which is 4, and that's going to give us a total resistance of 9 ohms. Okay, so moving on to the next one. So, again, why is this? I want to find the total current. Okay. So now what we want to do is we want to find what the total current is. I don't know why I have so many duplicates in here. Let's go ahead and calculate what the current is through the circuit. All right, so based off our previous answer on this question, we know that the equivalent resistance is going to have a value of 9 ohms. And so in order to find what the current is, we know that V is equal to IR. We're given what the voltage is here, so that's going to be 12 ohms. And so we can say that the current is going to be equal to the voltage divided by the resistance, which is going to be 12 over 9, which is going to be equal to 1.33. Okay? Amps. Okay? All right, so moving on. All right, now this question says 3 resistors in a circuit are with, well, that part's the same, but which is the best statement in regards to how much current passes through each resistor as shown? So read these and think about how the current through each resistor should compare to one another. All right, so let's go ahead and talk about this one. So this one, it's a little bit tricky when you think about it, because you think that, you know, these resistors all have different values. Maybe the current's going to be different. Maybe the current gets used at different rates through these. But it turns out actually that the current is identical through all of these, and that's the same as the current through the battery. Now, the reason for this is because the current doesn't have a choice of where to go, right? The only thing that alters the current is when you have an opportunity for it to split. So some of it can go this way, some of it can go that way. But something is perhaps different about these, but that kind of leads us into the next question. So let's look at, oh, maybe it doesn't lead us into the next question. I was sure that there was another question that had this. Maybe I inadvertently deleted it. This is not my day today, guys. So we can talk about what's going to be different here, and that's actually going to be the voltage across each one of these, right? So because these have different resistances and they have the same current, then the voltages should be different, okay? So now let's look at some cases where we want to find what the equivalent resistance is when these resistors are in parallel. I swear I had a question about this. So this is an example of when we want to add resistors in parallel. And so the way that we're going to do this is we're just going to add the reciprocals of the resistances. So in this case we have 3 ohms, 2 ohms, and 4 ohms. So this is going to be 1/3 plus 1/2 plus 1/4. Invert this afterwards to find the equivalent resistance, and this is going to be equal to 0.92 ohms. Okay? All right, on to the next one. Now what we want to do is we want to find what the total current is out of the battery. So go ahead and do that really quickly. All right, so we should have this one, right? So same kind of process we went through with the last one. Once we have the equivalent resistance, what we can do is we can say that the voltage is going to be equal to the current times the equivalent resistance, or the current is going to be equal to the voltage divided by the equivalent resistance. And so this is going to give us the answer of 13. No, this is the wrong question. Same question. I don't know what I'm doing today, guys. Oh, what I did was I have the editor open on this, but I have the slideshow here, so I've moved the edited version forward. So go ahead and put your answers in for this, but this is 13 amps about. Yeah, question?
How did you point IQ? Why did you raise that to negative?
It's because 1 over REQ is equal to 1 over R1 plus 1 over R2, and so we're solving for REQ. Yeah, yeah. Okay. All right, now change the right slide. So maybe 5 more people that need to put in their answers here. Okay, and we're at 45. Good. Okay, so now this question is asking us to compare the current through these resistors and to think about. I don't want to explain this one too much, but read this question and try to answer it, and we'll talk about it. All right, so let's go ahead and talk about this one. So what were some of the ideas we came up with? What do you guys think? What do you guys think?
So since the current's going to take the path of least resistance, it would go through, or R2 would have the greatest current.
Right. So the current's going to kind of bias itself in a way that more current's going to flow through the resistor with the least amount of resistance. And so that says in this case, this resistor R2 is going to have the largest current. Now let's look at the next question. So now what we'd like to do is we'd like to consider what the difference in electric potential is across each resistor and how that compares to each other. So go ahead and talk about this one. Okay, so let's talk about this one. Now, before I tell you what the answer is, I want to show you how we can think about it. So what we can do is we can draw this circuit. So we have our 3 resistors here. So this is R1, this is R2, this is R3, and we have our battery. So let's draw some loops to go around here. So go around like this, go around like this, and go around like this. So call this one loop A, loop B, and loop C. Now, if I write down the equation for loop A, but don't write it in terms of IR, we'll leave it in terms of V sub 1 to denote the potential across R1. Then this is going to give me V minus V1 is equal to 0, right? Because I start here, I increase potential, go across R1, decrease potential, and then I get back to where I started. B is going to give me V minus V2 for the same reason, right? Increased potential, come over here, decreased potential, which is equal to 0. And C is also going to give me something similar. So this is going to be minus V3, which is equal to 0. So we could rearrange these to solve for what V1, V2, and V3 are. And what we see is that V1 is going to be the same as V2, which is the same as V3. All of these are going to be equal to that same V that we started with at the beginning. Okay. So the answer here should be that the difference in potential across each of the resistors is going to be the same. Okay, so moving on. Now let's put what we learned together to find what the equivalent resistance is through this circuit, or for this circuit, and what the current and potential difference across each one of these is going to be. Okay, so take some time to work through that. Okay, so let's go ahead and draw this one and then solve it. So have our circuit here where all of these resistances are the same and they have a value of 3 ohms. This has a voltage of 12 volts and we have this last piece right here. So the first thing that we're asked to do is to find what the equivalent resistance is for the entire system. And so in order to do that, I'm going to kind of draw what it looks like in terms of the way that you're collapsing this. So the first step that you want to do is to take these two and combine them together. And so the circuit's going to look like this now. So this is R, R, R. This is going to be 2R. Okay. This is 12 volts. Now, the next thing I can do is I can collapse these in parallel. And so this is going to be 12 volts. This is going to be R. This is going to be, ultimately the value of this is going to be 2 volts, 2 ohms. I don't have this broken apart in pieces. So when I'll just do the calculation real fast. So this is 1/3 plus 1/6 inverted. This is a half, so this is 2. Yeah, this ends up being 2. So then you have something like this. So this is really 3 ohms. This is R is equal to 3 ohms. And this is R is equal to 2 ohms. So the last thing that we can do is we can add these in series. And so this is going to give us a value of 8 ohms ultimately. So REQ is equal to 8 ohms. So now that we have this equivalent resistance, what we can do is we can use it in conjunction with the equation V is equal to IR to find what the current is out of the battery. And so when we do that, we say that V is equal to IR, and so I is going to be equal to V divided by R, which is going to be 12 volts divided by 8 ohms. And so this is going to give us a value of 1.5. So we have 1.5 amps. Okay? Now that we have this 1.5 amps, what we can do is we can say that this is the current that flows through, this was the R1, so let's label these correctly. So this is R1, this one is R2, this is R3, 4, and 5. Okay, so let me kind of erase some of the extra stuff that we don't need so that we can make use of all of the room that we have here. So right off the bat, what we need to do is we need to find what all of these currents are. So we know that I1 is going to be equal to the 1.5 amps because all of the current that's coming out of this battery is going to go through here. I2 we don't know yet. I3 we don't know yet. I4 we don't know yet. But we also know that I5 is going to be the same 1.5. because the current's going to split here, right? So it splits here, but then it comes back together. And so this I5 is going to be the same as this one. Okay. Now what we can do there's kind of a couple of ways to look at this. But one of the things that's useful here is to think about how this current's going to come in. It's going to split in two pieces. And so if we look at it like that, we can say that, well, this has, this portion right here has half of the resistance that this has. But the sum of these currents is going to be equal to the current that comes into the junction in the first place. And so what I can do then is I can say that I1 is going to be equal to I2 plus I3. So that's the current junction equation that we can write. And then what we can do is we can try to set up some equation to solve for this, because we know what I1 is already. So I1 is just going to be the 1.5 amps. So in order to set up that equation, what we can do is we could draw some loop here. So if I draw this loop and apply some loop rule to this, what I can say is that I2 times R2 is going to be equal to I3 times R3 plus R4. Okay. Now, if we plug in what our values for our resistances are, this says is I2 is going to be equal to 2 times I3, right? And that seems to make sense, right? Because if all of these resistors have the same resistance, and there's 2 of them here, then this should have double the current that flows through that one. And so looking at this in conjunction with the value that we had here, so this is going to be 1.5 amps, the values for I2 and I3 that satisfy this and also sum to 1.5 amps are going to be, this is going to be 1 amp, and this is going to be 0.5 amps. And I4 is equal to the same thing as I3, okay? So the next thing that we can do is we can calculate what the voltages are across this. So we can say that V1 is just going to be equal to the current I1 times the resistance R1. This is going to give me a voltage of 4.5 volts. We can do the same thing for R2, and so R2 is going to be 1 times 3. So V2 is going to be equal to 3 volts. V3 is going to be 0.5 times 3. This is going to be 1.5 volts. V4 is going to be equal to V3, so this is going to be 1.5 volts, and V5 is going to be equal to V1. So we can write this like this. Okay. Now, this was just one of the ways that we could have gone about this. Another way to do this would be to apply some loop rule here, right? So if I apply some loop rule here, that would allow me to solve for what the voltage is across R2. And if I solve for that voltage across R2, what I can do is I can apply V is equal to IR in order to find the current through R2. So what you'll find in these kinds of problems is there's actually a number of ways to go about getting the right answer. All right, any questions about this one? All right, is that almost a question? No question? Okay. All right. So this is just a summary of the loop rules that we talked about last time, but I did want to show these slides because it's a nice depiction of what we talked about last time in terms of when you're going across a battery. This is going to be some increase in potential, so you can look at this like this hill, and this was kind of what I did with Roller Coaster Tycoon. So you get to this potential hill, you go up it, and then when you go across a resistor, you go down it. And then you can write your loop equation by looking at that. But you can also do the same thing for looking at these in parallel. So you still have to get back down to the same point. So if I start in this lower left corner, I go up the hill, and whether I go through the path in the middle or I go through the path on the outside, I still have to get back down to the same potential. And again, we could write our loop equations, and this is kind of showing the same thing again. Okay. So now we want to get back into doing some calculations with the loop rules again. So for this question, what we want to do is we want to choose the equation that best represents the left loop in the circuit shown here. Okay, so go ahead and take a couple minutes to look at that one. All right, so let's talk about this one. So I think these kinds of questions are actually easiest done without looking at them as multiple choice questions, but rather trying to figure out what the answer is first, and then refer to the answer choices. So if we draw this circuit, and we're going to use this one for the next one as well. So we have this kind of arrangement where there's a resistor, battery. Is there another resistor down here? No. So this is going to be our R1, this is R2, R3, R4, this is our epsilon 1, this is our epsilon 2. So what we want to do is we want to write some equation for this loop A that I have here, where this current I1 is labeled here, this is I3, and this is I2. Okay, so when we write this loop equation here, we're going to have A. This is going to say that delta V is equal to 0, which is going to be equal to this increase in potential from this, so this is going to be some epsilon 1, minus a decrease in potential across this one, so this is going to be minus I1 R1. We're going to have another decrease in potential across R3, so this is going to be minus I3 R3, and then this is going to be another decrease in potential to get back to where we started, so this is going to be minus something times R4. And the question is, what should this something be? What should this current be here? Think about it. Well, we could call it I4, right? It's kind of natural with the way that we've done this, because we had R1, we had R3, we have I1, we have I3. So we could call this R4, or call this I4. Why wouldn't we want to do that? Why wouldn't we want to call this I4? Yeah.
Because it's equivalent to I1.
Yeah, because it's the same thing as I1, right? So what we could do is we could draw our junctions here like this. And so this is, we call this I4, we call this I2, I3, same I3 that flowed through here, same I2 that flowed through here. But what we end up seeing when we write this junction is that I1 is going to be equal to I2 plus I3. And from the second junction, we have I2 plus I3 is equal to I4. And so that tells us that I1 is I4. And so this should be an I1, which is, this whole thing is equal to 0. Okay, so that's going to be answer choice E. So we're going to do one more of these real quick, and then that'll be it for us today.
Before you move on, so does the effect of the battery being there not, or like, so since I2 is going around, is the battery not affected in any way?
I2, or that epsilon 2 for the battery, that changes what the current was in the first place. So whether I have this battery here or not, like the value of the current would be different, right? So say if the E2 was here, or the epsilon 2 wasn't here, I2 was like 2 amps. Whereas if it is there, it's 1 amp. So that kind of sets what the values of these are, but it doesn't change the fact that the current's going to be constant through that portion of the loop, because that current doesn't have anywhere else to go. It just flows through the whole thing. If there was a split there, so if I had something like, for whatever reason, if I had something like that or something, if you want to get really crazy, right? Then the current here and the current here are not the same, right? But because the current, it's just kind of going along in this like tube, I guess you could think of a wire that way. It just kind of keeps going around like this. It doesn't have a choice of where to go. Okay? Yeah. What's up?
On an exam, would you give us the direction of the current? Because couldn't I2 technically be pointed the other direction?
Yeah, it could. It could. And what you would find if you solve this would be that you could have a negative sign, depending on the values of epsilon 1 and epsilon 2. There are various arrangements and situations situations you can have is epsilon 1 greater than or less than epsilon 2. You have the most boring situation if they're equal to each other, right? Well, actually, that's not necessarily boring in this case, but anyway. All right, so we don't have enough time for another one, so I'll let you guys go early, but yeah.
So does the current only change when, like, at a junction?
Exactly,
Okay.
exactly.